Okay, we're starting recording for section 1.8. So you now have learned a lot about the solving systems of linear equations. And you know a system of linear equation can be written as a vector equation, and it can be written as a matrix equation. And there are advantages to those types of equations depending on the application. So another way to think about linear algebra is in regards to introduction to linear transformations. Okay, so they say here the difference, and maybe I'll highlight it. Okay, one moment here. The difference between a matrix equation and the associated vector equation is merely a matter of notation. Okay, and a matrix equation, though, can arise in linear algebra in applications such as computer graphics and signal processing in a way that is not directly connected with linear combinations of vectors. We can think of the matrix A as an object that acts on a vector X. Okay, we can, let me just highlight that again, highlight this. Absolutely amazing. We can think, hold on here, sorry. There we go. So, hold on everybody, sorry. Okay, so we can think of a matrix, say, that acts on a vector X by multiplication when you multiply A times X to produce a new vector A times X. So let's look at an example here. Let's see what they're talking about here. One moment, let me get this off here. Okay, so you see there, you have a matrix A times a vector X. Now, what's the size of the matrix A? What's its size? How many rows, how many columns? Good, Mikhail. It's a 2 by 4. And you're multiplying a 2 by 4 matrix A by a 4 by 1 vector X. So the matrix multiplication is defined, and that will equal the vector B. And you actually learned how to multiply a matrix by a vector. You learned that earlier in chapter 1. So now also they have the matrix A times a vector U, and it maps the vector U into the vector 0. So you see what you're doing. If you look at the figure 1 below, what are you really doing here? You are taking vectors like the vector X and the vector U above that live in 4-dimensional space, and you are transforming those vectors into vectors that live in 2-dimensional space. Okay, you're transforming vectors via a matrix multiplication, and the matrix multiplication is a transformation. Okay, so that's how you have to think about this. So, well, first, are there any questions? Are there any questions at all on what you're seeing here? Okay, okay, very good, very good. Well, let us proceed on then. Okay, so let's go to an example here. And this, one moment here. Hold on, there was something. What you're doing, Mikhail. Well, let's look. I'll tell you. Let's look at this example 1. Let's look at this for a moment. So you see here, you have a matrix A. It's a 3 rows, 2 columns, right? And you can do a transformation from r squared to r cubed by this action, by taking the matrix A and multiplying it by the vector x. So let me highlight here what I'm talking about. So do you see below? A times x. Are we in agreement? Are we in agreement about this, about what you're seeing here? The matrix A times x is equal to, all right, so the vector x is a 2x1 vector, right? It has x1 and x2 as coordinates. And when you multiply that by the matrix A, which has 3 rows and 2 columns, you get a new vector. You get a new vector with coordinates x1 minus 3x2, 3x1 plus 5x2, and negative x1 plus 7x2. So you see in the picture to the left, in this picture to the left, okay, well, I mean, they say here in part A, find the image of U under the transformation. Find the image of U under the transformation. So if we look at the vector U, okay, and I'm going to part A here. If we look at this part, and I like to highlight things because then I think it helps it for the recording. The vector U has coordinates 2, -1. And under the transformation, you're taking that vector U and you're mapping it to the vector 5, 1, -9. And that's what they're showing. That's what they're showing in the picture on the left. That's what's going on. That's the transformation. Are there any questions on part A of this example 1? Okay, well, let's talk a little more. For B, they want you, in this case, to find a vector x in R squared whose image under the transformation is vector B. Let me see. You're not turning the matrix into a vector in part A. You are taking a vector U, and multiplying it by a matrix A. And that's defined as your transformation of the vector U. That's how your transformation is defined. So what the transformation does is it takes a vector U, which takes that vector U, which lives in 2-dimensional space. See the picture on the left, the vector U has coordinates 2, -1. And the transformation takes that vector and maps it into a vector 5, 1, -9 in 3-dimensional space. And that's what they have on the picture on the left with the vector, the coordinate 5, 1, -9. Take a look at it. Okay, thank you for that. Yeah, well, that wasn't, I'll tell you the problem. My younger brother doesn't have a cell phone, and occasionally I have to answer one of his calls. I call the house phone, so I apologize for that. The next time it rings, I'll just shut it off because I don't want us to be interrupted. This is our time. So okay, Mikhail, are you okay with that? With part A? Are you okay with that? And the picture there on the left? Okay. All right. All right. So remember like when you learned about functions, and a function maps elements of a domain to elements of a range. How many recall that? Mapping a function maps elements of a domain to elements of a range. Yeah, this is the same type thing. You have a domain of that's in R2, vectors with 2 coordinates. They live in R2, and the transformation maps those vectors into a range that lives in 3-dimensional space. It's the same kind of thing. It's just you're doing it with vectors now. And in part B, they say, all right, find a vector x in R squared whose image under the transformation is a vector b. Well, the vector b given above is 3, 2, -5. So in this case, what you have to do is you have to solve, okay, this matrix equation. Let me take this, unhighlight that. You have to solve the matrix equation. Okay, so you know a vector in the range. You're trying to find a vector in the domain. That's what you're doing here. That's what you're doing. When you find a vector x in R squared whose image under the transformation is a vector b. Okay, images are in the range. So, okay, you just go forth then and set up your, augmented matrix for this matrix equation, something you should know how to do, and solve for the vector x. And the vector x, you'll have 1.5 and -0.5. So the image of this vector x under the transformation is the given vector b. If you take that 3x2 matrix A and multiply it by the vector x, which has coordinates 1.5 and -0.5, you will have as its image the vector 3, 2, -5. Okay, so they're having you think about the concepts you learned in a new way. Let me see here. I think there's a question. 3, 2, -5, Mikhail, it comes from the example. In the example above, they give you vectors u, b, and they give you vectors u, b, and c. So 3, 2, -5. So now everybody can follow along in their ebook here. This is in your ebook also. So do follow along in the ebook. Have that open. Let me see here. Moving down. Yep, another call. Hang on one moment. Oh, hey, Alan, I'll have to call you back, okay? I'm teaching, okay? Yeah, I'll call you back tonight, I promise, okay? Thanks. Okay, so I'm popular, aren't I? All right. So, okay, I'm sorry. Let me just see here. Okay, I don't want to get too deep here into the weeds right now. I mean, I don't want to get too deep. I want to just kind of cover the basic ideas. I think let's just sort of hit the basic ideas. We can always come back to this problem if we need to. I'm just debating if we, hold on here. Yeah, let's keep moving forward here. I don't want us to get caught up into too much stuff here. So, okay, now what I want to do is talk about a geometric understanding of a transformation. So you see here in example 2, you have a 3x3 matrix. 3x3 matrix that has as its first row 1, 0, 0, as its second row 0, 1, 0, and third row 0, 0, 0. And if you take, so that 3x3 matrix will act on vectors that live in R3, because you can't have matrix multiplication defined unless the matrix A is multiplying a 3x1 vector. Okay. But you'll notice that when you multiply the matrix A by a vector with coordinates x1, x2, and x3, you see how the third coordinate, the vector in the image has a third coordinate of 0. You see that? So what you're doing is, well, if you look in figure 3, the pictures are great here, really. You see, what you're doing is you're taking vectors, okay, that are in R3, and they're being mapped into the x1, x2 plane in R3. So you're taking points in three-dimensional space and you're mapping them to points that are in three-dimensional space but are restricted to the x1, x2 plane. Okay, and so this kind of math can come up in computer graphics, and you're going to see that later on in chapter 2. But you see a little bit of graphics right here. If we look at example 3, okay, we're going to look at something called a shear transformation. Okay, so let's look at example 3 here. So here you have a sheet. You have a sheet there in the picture. And then you have a sheared sheet. So there's a transformation. Yeah, I don't know, Mikhail. That's a good question. But the matrix 1 with the rows 1, 3, 0, 1 will take vectors in R squared and map them to R squared. And this particular transformation using that matrix A is known as a shear transformation. That's what it's called. It can be shown that if T acts on each point in the square shown in figure 4. Okay, so figure 4 is, well, if we look below here, let's look below. Figure 4 is a little bit below. There's the sheep, and the sheep is made up of coordinates. The sheep is made up of coordinates, right? And if you transform those coordinates using the transformation A times X, the sheep is going to look like what you see there on the picture on the right. So, like, for instance, let's take a point like 0, 2. Let's take a point like 0, 2. Okay, now 0, 2. All right, if you look there in figure 4 on the left, the sheep is contained in a square. And the height of the square is 2. And to the right, so like the square is bounded by the lines x1 equals 2 and x2 equals 2. And if you were to take the corner point 0, 2, which is on the top, it's on the x2 axis. If you transform 0, 2, 0, 2 becomes 6, 2. Okay, so that point is transformed as you see in figure 2. And similarly, 2, 2, the image of 2, 2 is 8, 2. Okay, so let me see here if, well, yeah, is this okay? Is this all right? The picture below, figure 4, are we okay with what they're showing here? The point 0, 2 gets mapped to 6, 2, and the point 2, 2, which is the top right-hand corner on the left of the sheet, gets mapped to 8, 2. Yeah, it's right there, and I want to make sure everybody's comfortable with it. And the effect of this transformation is the sheep is getting transformed into this sheared sheep. Okay, and that's known as a shear transformation. And this is what they're talking about here. Are there any questions on that? Any questions in general on that? Okay. Okay, well, let's keep going then. Let's keep going. Whoops. So there's an important topic called linear transformation. So a linear transformation is linear if it satisfies the two conditions below. Okay, so if you transform the sum of two vectors, then that's going to equal the sum of the transformed vectors. That's the first condition. And the second condition is if you transform a constant times a vector u, well, you can bring that constant or scalar outside. And by the properties of matrices, when you multiply them by vectors, okay, these two properties are true for when you take a matrix and multiply it by a vector x. And they denote the transformation symbolically this way. Okay, you're taking a vector x and you're hold on. Yeah, you're taking a vector x and you're mapping it into the vector a times x. That's what that means. And by the fact that the matrix A times U plus V is equal to the vectors AU plus AV, and the fact that the matrix A times a scalar times a vector U means you can pull out the scalar, so you get C times A times U. This means that the matrix transformation is a linear transformation. It can be classified as a linear transformation. Okay, so, and there's some important properties that can be shown for linear transformations. There's some important properties, and here are two of them right here. If you transform the zero vector under a linear transformation, you get back the zero vector. Also, if you transform a linear combination of two vectors, that's property 4 there, that'll equal a linear combination of the transformed vectors. So those are important properties. Those are important properties. Let's see how it relates to example 5. So examples are really helpful. How many, by the way, had to I think you had to pay for your My Math Lab today, right? I think the trial period's over, I believe. Is that correct? Okay, all right, Mr. Marcel. All right, so all right, yep, gotta get out the credit card now. But hey, you're gonna get well your value for my math lab. You're gonna get well. I mean, this you're using one of the best textbooks with best online, great online homework system, and and I'm actually using it to give exams that students can be comfortable on. You know, so okay, here we have a linear transformation. Here we have a linear transformation in example 5. And we want to find the images under the transformation of vectors u, v, and u plus v. So look what they did below. They found that the transformation of the vector u is -1, 4. The transformation of the vector v in the solution is -3, 2. And the transformation of the vectors u plus v is -4, +6. Okay, now they note that the transformation of the sum of the vectors u plus v is obviously equal to the transformation of u plus the transformation of v. If you add t of u and t of v, -1, 4, that vector, and the vector with coordinates -3, 2, that adds up to -4, 6. Pictorially, this is what's going on. Pictorially, you're actually doing what's called a rotation transformation. But this is what's going on. So you see there, you have your vectors, you have your vector u and your vector v and u plus v. And you transform the vectors into so you have that parallelogram on the right. Okay, you're transforming that parallelogram to a parallelogram rotated 90 degrees counterclockwise about the origin. Okay, and that's what you have. That's what you have there. If you look at the vector u, like in that picture there, look at the vector u and look at the vector t of u. What's the angle between the vector u and the vector t of u in this example 5, figure 5, or figure 6, I should say? What's the angle look to be? Yeah, 90 degrees. That's right, Mikhail. And if you look at the vector v, that's right. And if you pi over 2, good. And if you look at the vector v and the transform vector v, what's the angle look like to be there between those two vectors in the picture? Good, Belen. Also 90 degrees. Also 90 degrees. So that's why they call this a rotation transformation. Now, one more. Look at the vector uv on the right and look at the transform vector uv. Look at the dots, the black dot and the blue dot. What's the angle between those two vectors? So there's the vector uv in figure 6, and then on the right, and then look at the transformation of uv, that vector. What is it? What's the angle? That's right, Cameron, 90 degrees. 90 degrees. That's right. So that's why they call this a rotation transformation. And so this is just, it's another way of thinking about, like, if you take a matrix and multiply it by vector x, you're really doing a transformation on that vector. And in this case, you're transforming vectors from two-dimensional space to two-dimensional space. But depending on how the matrix is defined, you can transform vectors from, a certain space of some, like m dimensions, to another space of n dimensions. Okay, or they have it really as you transforming a vector from n dimensions to a space of m dimensions. That's what they actually have here. If I go back here to figure, I'll find it here, figure 2. One moment. There. That's sort of that's the picture. So these are helpful, uh, uh, certainly helpful. Okay, are there any questions on that? Okay, if we're good on that note, let me stop the recording.